Hi, I am Syifaa and I will be explaining on the content of Reaction Engineering 1 subject. The objective of this subject are to propose type of reactors and catalysts, to describe the process operation of reactor separator unit, to propose strategy to increase selectivity and yield of hydrogen, and last but not least, to calculate the size of reactors. Hydrogen is produced widely by catalytic steam methane reforming (SMR) process. In this process, there are three main reactors that being used, which are steam methane reforming (SMR) unit, water gas shift (WGS) unit, and PSA to produce hydrogen with more than 99% of purity. For reaction engineering subject, we will be focusing on SMR and WGS reactor. Ding and Alpe 2000 claimed that in conventional SMR unit, conversion of methane to form hydrogen was performed in a fluidized bag reactor containing nickel-based catalyst. Nickel, which is the non-precious metal, was used widely because SMR are limited to less than 5% catalyst efficiency. Meanwhile, Halliday et al. 2009 mentioned that the reaction in WGS could be achieved in a conventional plug flow reactor with the most common catalyst used, copper-based catalyst. Both fluidized bag reactor and PFR can be represented by ideal PFR in simulation. Thus, in this project, we will be using PFR to demonstrate our model. Hydrogen production in SMR process mainly involve two main reactions, which is in SMR and WGS unit, and then followed by absorption process by PSA unit. The diagram of general SMR process is as above. Firstly, let's focus on SMR unit. Steam reforming is a catalytic process which involves a highly endothermic reaction of natural gas, mainly methane, and steam. Wang 2012 mentioned that this reaction usually happens at a high temperature of 800 to 1000 degrees Celsius and at pressure of 14 to 20 atm. In SMR, methane reacts with steam to produce hydrogen and carbon monoxide, with the presence of nickel-based catalyst. Since SMR produces a big amount of carbon monoxide, the gas will then pass through WGS unit to decrease the amount of carbon monoxide while increase the hydrogen content. For this reaction, copper-based catalyst was widely used. Carbon monoxide will react with steam to produce carbon dioxide and hydrogen. The product from the reaction in WGS still contain quite high amount of carbon monoxide, carbon dioxide, and methane. Thus, the gas are then enter pressure swing adsorption (PSA) unit to obtain hydrogen with more than 99% purity. The first strategy is to increase the concentration of methane and reduce the concentration of carbon monoxide. Based on the selectivity formula above, in order to increase the selectivity of desired product, hydrogen, Ca, which is the concentration of methane, should be increased, and meanwhile, Cc, which is the concentration of carbon monoxide, should be decreased. Next is to have a high operating temperature. This is because the undesired reaction has higher activation energy than the desired reaction. Thus, the operating temperature of this process should be as high as possible to increase the production of hydrogen. Lastly is to increase the operating time of the SMR process. As shown in the graph, hydrogen, which is a desired product, increase over time. In longer time, the reactants will completely be converted into hydrogen. Hence, the concentration hydrogen will increase and more hydrogen will be produced. The sizing of reactors can be calculated by using 5-step method, which is step 1 mole balance, step 2 rate law, step 3 stoichiometry, step 4 combine, and lastly step 5 evaluate. The target of this project is to produce 30,000 tons per year of hydrogen. Thus, the information needed for the volume calculation was calculated accordingly. The reaction in SMR and kinetic data used are as above. The volume of SMR was calculated by using formula of PFR volume and by using 5-step method, and this resulting to the volume of 25.2176 meter cube. For WGS, the reaction and kinetic data used for the calculation are as above. The volume of WGS was also calculated by using formula of volume of PFR using 5-step method. The volume of WGS calculated was 9.6692 meter cube.
Hi, I am Jia Yi. I will continue with the conclusion of this chapter. First, the type of reactor used are plug flow reactors, and the catalysts used are nickel-based catalysts and copper-based catalysts. The SMR reaction occurs at a high temperature. Then the product gas mixture will pass through the second plug flow reactor where WGS reaction takes place. Both reactions are complex reactions. The gas then enters pressure swing adsorption (PSA) unit. We had come up with 3 suggestions to maximize the selectivity and yield of hydrogen. The volume of both reactors was successfully estimated and are shown in the slide.
Hello everyone, I am Arash. Jia Yi and I will be explaining the contents for CEB 2053, Process Modeling and Simulation. The objectives of this section are to simulate the steady-state reaction process using process simulation software based on the process parameters from Reaction Engineering 1, to validate the simulation by comparing the values obtained from the simulation with manual calculation using reaction system from Reaction Engineering 1, and to perform sensitivity analysis by discussing the effects of pressure, temperature, feed flow rate, and composition on the reactor performance. As shown here, this is the process flow diagram conducted via symmetry. Two assumptions are made in this simulation, which are only pure methane exists in the natural gas stream and that the mixture produced behaves as ideal gas. These are the summaries made on the streams and utilities in the simulation.
This is a simplified version of the process flow diagram for SMR and WGS unit. Two reactions are involved in the entire process. The first reaction occurs in the first plug flow reactor and followed with the second reaction in the second plug flow reactor in series. Before developing the mathematical models, a few assumptions should be made to simplify the calculation. All the assumptions made are shown in this slide. These are the mass balance, rate law, component balance, and energy balance equations developed based on the reaction in the SMR unit and assumptions made. While these are the balance equations developed based on the reaction in WGS unit. To identify the simulation, we can compare the manual calculation and simulation by calculating the deviation error. The deviation error can be calculated using the formula shown. From this table, a relatively high deviation error is seen when comparing the manual calculation and simulation outlet flow rates at both SMR and WGS reactors.
In the third part of this course, we have conducted a sensitivity analysis on 4 independent variables, which are pressure, temperature, feed flow rate, and composition on the chosen dependent variable as summarized in the table. Case study 1 shows the effect of pressure on the outlet flow rate. The independent variable is the pressure of natural gas feed, while the dependent variables are listed as shown. Two graphs are plotted from the data obtained. From the simulation, it is observed that as the pressure increases, the molar flow rate of SMR and WGS also increases. From the ideal gas law, we obtain PV equals to nRT. The inlet of the PFR can also be represented as ideal gas law as shown. By rearranging the two equations, we obtain the third equation where we observe that as the inlet pressure of the PFR increases, the volumetric flow rate also increases. This indirectly increases the molar flow rate. In case study 2, we observe the effect of temperature on the outlet flow rate. The selected independent variable is the temperature of natural gas feed. The dependent variables are the mole flow of carbon monoxide and hydrogen in the SMR outlet. From the simulation, it is observed that the outlet molar flow rate of CO and hydrogen increases as temperature increases. As the reactions that take place in the SMR is endothermic, hence it favors high temperature condition. The increase in temperature supplies more heat energy, which pushes the equilibrium forward and produces more product.
Case study 3, effect of natural gas feed flow rate. A graph of molar flow rate of hydrogen in SMR and WGS outlet against the feed flow rate of natural gas is obtained and shown. From the graph, it can be noticed that when the feed flow rate increases, molar flow rate of hydrogen in both SMR and WGS outlet increases. This can be explained by the equilibrium constant equation of the reactions in SMR and WGS. Given that the temperature and the total pressure are kept constant, when we increase the mass flow rate of methane in the feed, it will lead to an increment of methane composition. Hence, by rearranging the formula, when the composition of methane increases, the composition of the products in the SMR also increases. This affects the products produced in WGS, as the reactants used in the WGS are the products of SMR. Thus, will increase production of WGS. Case study 4, effect of composition of methane in the natural gas stream. A graph of molar flow rate of hydrogen in SMR and WGS outlet against the composition of methane in the natural gas feed is plotted and shown at the side. From the graph, it can be observed that when the composition of methane in the natural gas feed increases, molar flow rate of hydrogen in both SMR and WGS outlet increases. This is because the increment of composition of natural gas indicates higher purity and concentration of methane. When the concentration of methane reactant is higher, rate of reaction is higher, and more products are formed because more reacting molecules or ions are available. Therefore, the flow rates of the products will increase. Also, the outlet molar flow rate of hydrogen in WGS is always higher than that in SMR because the production of hydrogen in SMR will accumulate and it flows through WGS where second reaction occurs and produces more hydrogen. In conclusion, we have successfully completed 3 main objectives for this part. First, we have simulated the steady-state reaction process using symmetry software. As for the model validation part, we have a very high deviation error, and the possible reasons for this outcome are epistemic uncertainty, inaccurate values from articles, unsuitable assumptions made in manual calculation, and human error. Last but not least, we have run 4 study cases to study the effect of pressure, temperature, feed flow rate, and composition on the reactor performance.
Hello, my name is Atiqah Syazni. I will be presenting for the part of separation process. In order to achieve a higher purity of the hydrogen production, the gas mixture needs to be purified by the H2 enhancer unit. The enhancer unit used is the adsorption system. According to CIRCA, adsorption process can be defined as the separation that is based on the selectivity of the solid adsorbents to one or more component of feed mixture. In the production of higher purity of hydrogen gas, pressure swing adsorption process will be used, but the process is carried out at higher partial pressure. In this chapter, I, together with Munirah, will be presenting the design of the adsorption column, the isotherm, characteristic of the adsorption column, and the strategy to produce 99.9% purity of H2 production.
I am Munirah Fatihah, and now I will be presenting about the design of separation unit. Firstly, for the type of separation unit, we use PSA since it is low cost and energy efficient. In PSA, there are 2 main processes, which are adsorption at high pressure and regeneration of adsorbent at low pressure. Next, for the configuration, we use 6-type layered double bag PSA. And finally, for the materials, we use low carbon steel since it can reduce capital costs and have low corrosion problems.
Other than that, in the PSA process, we will be using activated carbon and zeolite 5E as the adsorbents. Activated carbon is a highly porous material that can provide a large surface area, which make it an effective adsorbent. Meanwhile, zeolite 5E, where 5A represents the porous opening with 5 angstrom, zeolite 5E has well-defined structures that can separate gases by using their molecular size or polarity.
Next, the isotope that is suitable for the adsorption of carbon monoxide, carbon dioxide, methane, and hydrogen gas is Langmuir isotope and loading ratio correlation (LRC). A previous study by Yabari et al. Has mentioned that Langmuir isotope show better result to fit the adsorption data for activated carbon, while LRC for the zeolite 5e.
Now, I will be presenting about the design of adsorption column. The assumed value for the properties of adsorption bed is as in the slide with the justification from literature. Next, for the total bed height, it is assumed to be 100 cm according to literature, and for the internal and external diameter, we choose a greater diameter so that more adsorbent can fit in the column and absorb more CO2. Next, for the mass transfer zone MTZ, it is a region in the bed where adsorption can occur. It is also represented by the height of unused bed. To calculate the height of unused bed for activated carbon, the 4 steps as in the slide can be performed, and at last we find the value for height of unused bed, which is 26.0 cm. Meanwhile, for zeolite 5e, the same 4 steps can be performed and we obtain the value of height of unused bed is 10.0 cm. The height of unused bed represents the MTZ mass transfer zone.
Moving on to the strategy in achieving 99.9% hydrogen purity. This part is divided to another 2 sub-parts, which are the hydrogen production and the desorption or regeneration process. For the first part, 2 strategies is proposed to achieve higher purity in H2 production. Firstly is by producing a 2-layer bed. The 2-layer bed consists of activated carbon at the first layer, while zeolite at the second layer. By doing this, we can maximize the adsorption process of CO2 at the activated carbon. Meanwhile, zeolite at the second layer will absorb the impurities left from the first layer. Secondly, using multi-bed for the PSA process will be a good strategy to enhance the purity of hydrogen gas. Hence, the PSA process will be operated in a cyclic manner where each bed will undergo a sequence of steps repeatedly. An example provided from the literature is 5 bed with 11 steps PSA processes. In addition to that, for the second part, I will present to you 2 strategies for the desorption or regeneration process. Firstly, regeneration can be done by lowering the partial pressure of the selectively adsorbed component over the adsorbent. Since the PSA used is in higher pressure, the reverse action will give reverse impact to the adsorbents. By doing this, the equilibrium loading of the adsorbent will be decreased. Other than that, desorption process can also be done by solvent desorption. For this method, the adsorbent will be treated with the eluting agent to remove adsorbed component from the used adsorbent. There are 4 steps in this method, including firstly, washing adsorbents with water, treating adsorbents with eluting agent, stirring, and lastly, washing the regenerated adsorbent with water.
To conclude, there are 4 main parts for separation process 2, in which the first one is the design of separation unit. We use the pressure strain adsorption PSA. Then the second one is adsorbent and isotope, in which we use activated carbon and zeolite 5A. That is mapped into Langmuir isotope and LRC isotope. Then for the third one is the design of adsorption column. The data value obtained and calculated value is as in the slide. And for the last one is the strategy to produce hydrogen with a purity of 99.9%, in which the first one is we can use more than one adsorbent. The second one is multi-bed PSA. And then for the strategy for the regeneration of adsorbent process, we can lower the partial pressure of selectively adsorbed components over the adsorbent, and the second one is solvent desorption. Therefore, all of the objective has been successfully achieved, but that is all for separation process 2 section. Thank you.
Throughout the whole of the process of completing the integrated design project, there are few things that we can reflect on. Firstly, for the first aspect, what we can reflect is to think on how we can produce the hydrogen gas from natural gas using steam methane reforming technology. Since it is not an easy task and requires a lot of research, we decided to distribute tasks and provide a timeline for our progress. Next, we also feel excited since we can practice applying what we have been studying over a few months. However, in the middle of completing the project, there is also a few things happen, such as the simulation is not working, clashing with other assessments that makes us struggle a lot to complete all together. With the help of the team members, we finally completed the project before the deadline, despite of the exhausting phase experienced by us. Other than that, for the evaluation aspect, what can we reflect is the importance of right understanding of each team member. Few adjustments need to be taken into account to find the right solution, and some parts need to be redo for multiple times. By having right understanding about the project, it will help us to complete the project faster. In the analysis aspect, what can be done to improve the progress of completing the project is by having discussions with other classmates and from the lecturers. The things that make it difficult is because of the different free times of each member, along with other assessments that also need to be done. However, all the group members cooperated well, that results in the success of project completion. Next, it can be concluded that we should think from different perspectives. It is not always a way to solve a problem. We can also at least try by using trial and error. Another thing that can be reflected on is reading the research paper that have been done previously also give a big help for us. Lastly, for the action plan, if a similar situation happens again, we should have a proper planning and better time management. It also would be better to discuss more with the teammates and lecturer. Other than that, having strong basic concepts on the subject will also improve the working progress.